Hey everybody. Um, Sorry I'm not there today, but this is kind of a quick little notes intro to what you're doing today, and then the lab is pretty easy. I'll show you the lab here coming up. So, first off, your warm up. Hopefully you did the warm up, and hopefully you chose blue. Yes, blue light has the most energy. Think about the spectrum of all the electromagnetic waves. Start out with radio, and then you go to microwave, then you go to infrared. Then we have the visible light, which is broken out into some different areas. Then you have UV light, X-ray, and then gamma ray. So those are the different things. We go from low energy to high energy. Kind of crammed it in there. And in the visible range, you go from red, orange, yellow, green, blue, and violet. Remember, we're anti-indigo this year. And so the red is going to be closer to the lower end than the blue. So the blue is going to have more energy than red. And I'm going to prove that here with how we calculate the energy of light waves or light particles. Welcome to light can be both a particle and a wave. It has properties of both things. Remember, waves have wavelength and frequency and velocity, where particles can have kind of mass, velocity. I don't know if light really has mass. It does have a little bit of mass, but we're not going to get into that. Energy, things like that. So we can calculate, and then also it does this kind of quantum thing that particles do as well. So light has, let's just say that light has both wave and particle properties, and this energy aspect of it is a particle nature of light. So we're going to treat light. This is called the photon. A photon of light is a particle of light rather than a light wave. And they have energy. So the key here is that the energy is based off the frequency. Energy is based off frequency. So energy comes from frequency. How quickly is that electric field moving back and forth, and magnetic field? And so we'll use that to calculate it. The equation to calculate the energy of a particle is just the energy, E, equals a constant, H, which is Planck's constant, times whatever frequency the light is. So let's write those down. E is the energy. Now, we're going to use something called the electron volt, EV, electron volt, for energy. It's way smaller than a joule. Joule is way too much energy to talk about a particle of light. So we need something really small. It's like a meter being way too big, a distance to measure atoms or something like that, right? We wouldn't use a meter. We use nanometers. Same thing. We use electron volts for the energy of light particles because there's so little energy in a single light particle. H is Planck's constant. We'll get to that in a second, exactly what it is. And F is the frequency of light. And we're just going to stick with hertz for that, Hz. So back up here to H. H equals a constant. For this particular setup with electron volts and hertz, it's 4.14 times 10 to the negative 15th. And I'm going to put a box around that just so you know it's there. Now that and this equation and that constant are on your equation sheet. And we can calculate the frequency of light from that. So let's do that. If I wanted to calculate the energy for red light using a frequency of red light, then, because remember frequency gives it its color, then I say that energy equals HF. And so it equals 4.14 times 10 to the negative 15th, really small, times a large frequency, 4.3 times 10 to the 14th. All right. And when I multiply those together in my calculator, you can try it out as well, I get 1.78 EV, electron volt. Remember, it's going to come out as electron volt with this equation. And so that's the energy for a particle of red light. Well, what's the energy for a particle of blue light? We're going to do this a little bit different. There's an easier equation if we use wavelength. Now, wavelength doesn't always work except that we'll always work in this class because we're never going to do this in water or some other material. We're always going to do this in air or a vacuum. So the wavelength and frequency go hand in hand with the speed of light of 3 times 10 to the 8th. If you change the speed of light, it changes the wavelength, but we're not going to do that for this energy of light thing. We're only going to do that for refraction. And if you understand changing medium means changing speed and changing direction, then that's good enough for that. We're going to stick to doing it all in a vacuum here. So we have another equation that says the energy of light is equal to h, some Planck's constant again, but this time times the speed of light, hc, divided by the wavelength of the light. So it's a little bit different. There's more constants, but we're going to have a constant for hc that's a very easy number to use. So once again, E is the energy in electron volts, and hc is a constant. We'll get to what that is in just a second. And then the wavelength symbol is, well, the wavelength, and that is going to be measured in nanometers. Now, I know I spent a whole bunch of time telling you to convert nanometers to meters. For this equation, don't. Leave it in nanometers because our constant for this equation uses nanometers. And we get a nice easy number of 1240. The constant is 1240. Planck's constant times the speed of light using nanometers gives us 1240 as our constant. And so we can use that to calculate the energy based off wavelength for different light. So let's do that for blue. Energy is equal to hc over wavelength. That's going to be 1240 divided by a wavelength of 475. Look at that. That's easy math right there. And that will give me an energy, when I calculate that, of 2.61 electron volts. Now, notice that is a larger number, a little bit more energy than the red light. Is it twice? Yeah, it's about twice. No, it's a little less than twice. Twice would be 3.4. So it's not twice the energy of red light, but it is more energy than red light. And so the second half of today, you're going to jump over to a lab and see what happens when different energy of light particles hit a piece of metal. So if you're looking at the notes here, this is the beginning of the lab. Now, please, yours looks a little different than this. Please do this lab in Classkick. I know the directions say that, but do it in Classkick. Don't do it on the piece of paper, even though all the stuff you need is on the piece of paper. Please do the lab in Classkick. Classkick's got a little bit better directions, and you should be able to easily go through it. Please do the lab in Classkick. Now, the lab itself has you start out with question 1. You're going to calculate. So you're going to do one more example on your own. Show me that you can calculate. Again, in Classkick. Do it all in Classkick. Question 2, 3, and 4, you're going to manipulate the lab itself and see what happens when you shoot a couple particles of light at a piece of metal. What's going to happen to that metal? I'm going to show you here in just a second the key idea, just in case you're like, I have no idea what's going on. I'll show you at least the minimum of what you're supposed to see. And then you can change some things. You can change light intensity, which is what question 2 is asking you to do. You can send the wavelength more towards red, or you can send the wavelength of the light produced more towards blue, violet, and the ultraviolet here. Now, I do want you to focus on this. This section is the UV. So you can find 1, 2, 3, 4, 5 different areas in here. 5 different UV spots that you're going to test on your data table. Again, I'll show you again, but when it goes to UV1, UV2, UV3, UV4, and UV5, you need to put the slider in different spots up there in the UV section there. And please tell everybody at your table and maybe everybody else in the room, if you catch this point, that's how you do the different UVs. The other ones make sense, but for UV, please put it at different spots within that UV there. All right, the simulation itself is a little light gun shooting different light waves at this zinc. Now, nothing's happening. What we're looking for is this idea that eventually these little energy particles, let's slow it down a little bit, right? These energy particles hit, and when they have enough energy, right? There we go. See, when they have enough energy, they're going to eject electrons. This is what we're looking for. These light particles have energy. They hit the atoms of the metal and they eject the electron. I can't write on this. They eject different electrons. And so then you watch those electrons and you write down the biggest number you see for the energy when you're doing the lab. So this is what we're looking for. This is called the photoelectric effect. It's when light hits a piece of metal and ejects an electron, which, by the way, this is solar power. I can capture these electrons and I can send it through a wire and create electricity. This is how solar power works. And so we're studying the idea of light creating electrical energy through this thing called the photoelectric effect. All right, labs in class kick. Please do the lab. Make a group whiteboard on your whiteboards and just screenshot it and drop it into, I think, the last slide or just into class kick, or excuse me, into Google Classroom. Everyone have a good one, and I will see you all tomorrow.